Following James Webb, another super telescope has been launched. Euclid has opened its eyes, and what ESA's new space telescope has seen is shocking everyone. We have never seen so many galaxies in one place, at such unprecedented depths, and with such clarity. Euclid is expected to provide nothing less than definitive proof of the existence of dark matter and dark energy, while the images from James Webb once again cast doubt on the existence of both phenomena. Does this mean that the Euclid mission is doomed to failure from the outset? On March 19, 2025, the European Space Agency, ESA, published the first comprehensive data from the Euclid mission, a significant milestone for modern astronomy. The Euclid Space Telescope, which has been operating in space since July 2023, was launched with the aim of observing invisible dark matter and dark energy. The data now published includes breathtaking deep-field images in unprecedented 4K quality. These images not only show razor-sharp galaxy structures, but also provide glimpses of regions of the universe that were previously literally shrouded in darkness. Among the images are famous objects, such as the Horsehead Nebula, which appears in unprecedented detail thanks to Euclid's new resolution, and the Perseus Galaxy Cluster, a gigantic cluster of galaxies visible on a large scale for the first time. Particularly impressive about the telescope's performance is the sheer number of galaxies that Euclid has scanned and imaged in the first analyzed sections of the sky. In the first segment alone, over 26 million galaxies were identified, and that is still only a fraction of what the mission will capture over its planned 6-year lifetime. Some of these galaxies are up to 10.5 billion light-years away, which means that we are seeing them as they looked only a few billion years after the Big Bang. This also makes Euclid a kind of time machine that beams us directly into the structures of the deepest cosmic past. The enormous depth of data will enable researchers to reconstruct the large-scale distribution of matter in the universe, from which scientists hope to draw conclusions about the previously invisible dark matter. At the same time, analysis of cosmic structure formation should also provide clues to the true nature of dark energy, this mysterious phenomenon believed to be responsible for the accelerated expansion of the universe. It has not yet been proven from a strictly scientific point of view. With this first publication and the incredible images, Euclid has already demonstrated its scientific potential so impressively at its premiere that it's certain this mission will open another door to a new era of cosmology. Euclid versus James Webb. Different visions of the cosmos. The goals of the Euclid mission are ambitious. In some ways, Euclid's mission sounds similar to that of the James Webb Space Telescope. However, ESA is pursuing a completely different central scientific goal: to precisely map the large-scale structure of the universe in order to better understand the nature and distribution of dark matter and dark energy. Webb, on the other hand, is designed to image the first objects and structures of the young universe. Unlike traditional telescopes, which observe specific objects at specific points, Euclid is designed to create a systematic large-scale picture of the development of cosmic structures across billions of light-years. The mission's main goal is to build a three-dimensional map of the distribution of galaxies in the universe, with the space telescope recording both the positions and distances of millions of galaxies. This distribution allows conclusions to be drawn about the distribution of dark matter because, although it's invisible, its gravitational pull influences the movement and accumulation of visible matter. Euclid can therefore indirectly measure where dark matter is located by observing how light from distant galaxies is distorted by gravitational lensing effects. Researchers call this technique weak gravitational lensing analysis. Another central goal of the mission is to study cosmic expansion. In this respect, the mission is similar to Webb's, but Webb's instruments are not designed to directly observe the expansion of the universe. Dark energy is considered to be the driving force behind the accelerated expansion of the universe. There must, therefore, be observable connections between expansion and the movement and clustering of galaxies in the cosmos. After all, it was the movements of galaxies that led to the theory of cosmic expansion about 100 years ago. Euclid will reconstruct the history of cosmic expansion by measuring galaxy clusters and their redshift, thereby determining how the effect of dark energy has changed over time. The mission must proceed with the utmost precision. The instruments are designed to detect even tiny distortions in the light path. The initial data has already shown that the telescope's accuracy and calibration are sensational. Euclid's approach not only allows for precise measurements of the cosmic web and the large-scale distribution of matter in the universe, but also offers the opportunity to test the main ideas of currently competing and sometimes contradictory cosmological models. Even if Webb is right, Euclid still matters. In the long term, Euclid will provide a map of the universe and an immense database that, together with Webb's data, will help to clarify the two greatest unknowns in modern cosmology. We have no choice but to explore dark matter and dark energy in this data-driven way. Meanwhile, Webb's mission has provided further images that cast doubt on the existence of these two forms of energy and matter. Are the missions, therefore, in competition with each other? No, say the scientists. Even if Webb proves that the structure and nature of the universe is completely different before Euclid has completed its entire map, the mission will not have been pointless. A detailed and extremely sharp 4D map of the universe serves far more purposes than just proving the existence of dark matter or dark energy. The images will show billions of galaxies. The knowledge gained about their locations, movements, and dynamics alone will provide valuable clues about the nature and structure of the universe, even beyond the dark spheres. So, which telescope is better? Even though the name Euclid is not as well known as James Webb at the moment, the mission will change our view of the universe just as much as Webb's. The Euclid Telescope and the James Webb Space Telescope are both groundbreaking observatories, but they have fundamentally different missions. Euclid focuses on exploring dark matter and dark energy by mapping the large-scale structure of the universe and analyzing the effects of gravitational lensing. It provides precise 4D maps of billions of galaxies to understand cosmic expansion and the distribution of matter. Webb studies the earliest galaxies that formed after the Big Bang and analyzes the atmospheres of exoplanets to search for signs of extraterrestrial life. Thanks to its large mirror and infrared technology, Webb can look deep into the past and receive light from the first stars and galaxies. Key technical differences. Wavelengths. Euclid, optical and near-infrared. Webb, fully infrared. Mirror size. Euclid, 1.22 meters. Webb, 6.5 meters, much larger light collecting capacity. Instruments. Euclid, 600 megapixel camera and near-infrared spectrometer. Webb, NIRCam, NIR spec MIRI. Primary purpose. Euclid, wide field mapping and structure analysis. Webb, deep space imaging and exoplanet study. Mission duration. Euclid, at least 6 years. Webb, at least 10 years. What's next? 3 new super telescopes. Webb and Euclid are already superheroes of space exploration, but they are only the beginning. NASA, ESA, other space agencies, and private investors are already preparing to launch the next generation of super telescopes. 1. SphereX, 2025. NASA mission. Spectrometer for the history of the universe, epoch of reionization, and ICE's Explorer will map the cosmos on an unprecedented scale with over 9 million line-of-sight observations. We'll study frozen substances like water, CO2, and CO, key to the emergence of life. 2. Vera-C Rubin Observatory, late 2025. Ground-based 8.4-meter telescope in Cerro Pachón, Chile. Designed to study dark matter and map the entire night sky with incredible depth and frequency. 3. Nancy Grace Roman Space Telescope, late 2020s. Successor to Hubble, named after the mother of Hubble. Will have a 100x larger field of view than Hubble. Will study dark energy, exoplanets, and cosmic structure. Features advanced coronagraph technology for directly imaging exoplanets and analyzing their atmospheres. Subscribe now and be there for every new video. The next chapter of cosmic discovery has only just begun.